Any questions before we start? Let me remind you all that I will not be here on Friday. You'll have a guest lecture. Math Club will be Friday at 5 o'clock. Ansa's speaking. If you've ever seen her speak, she's fantastic. And she also added a PS to her talk that she wants to go to the science picnic too, so the talk won't be too very long. So got that going on. The math ends Saturday, 10 a.m. to 5 p.m. I hope that you all can show up to help out. That'd be wonderful. Sign up again, or you can drop in. Also, if I've still got your homework due on Friday, but I'm gonna be out of town. If anybody needs some tweaking, Saturday is a good day to do it. I'll be in my office during Kyle's week, Monday and Wednesday. So just email me if you're having a problem getting in on time, and I can help you fix that. Don't forget to do the evaluations as well. Please do that. Yes. Oh, I thought you raised your hand, but you turned your head. Okay, questions? Okay, so let me give you a good example of an invertible line. This is like really kind of groovy because isoverbal, you don't, in terms of an ordinary ideal, you can think of it this way. If there exists another ideal such as, so let me give you an example. And I'm also going to use this example to kind of tie in with how invertible ideals and so forth, how they factor into this. So let's look at R. This thing here, this is kind of a classical old chestnut. How many of you have ever seen this example, maybe in an earlier course, number theory or algebra or something, where they use this to show that you don't always have unique factors? Has anybody ever seen this? So, and this is the way it works. There's the easy factor equation, one we're all used to. But this one also has this factorization. Oh, looky, 6 can be factored these way. Now, I'll play this very fast and loose because before I try to convince you that this is actually not a unique factorization, there's some things that I really need to do. Can anybody tell me what I've kind of left dangling in the breeze as far as details?
I mean, you show that your 3 and 2 are irreducible.
Okay. I want to show that all those players are irreducible, right? And there's another thing. Let me show you another hazard. Look at this ring right here. Notice, by the way, that this ring does contain square root of -3, right? Is this bad factorization? In principle, it looks very similar to the other, doesn't it?
Oh, in this one, our second one, they're unit multiples.
Very good, very good. Notice that, let me do this right here. I wish I had used the minus on this. Notice that what happens when I take this right here and multiply it by this thing? I get what, 4/2, which is 2. And this is actually a unit. Right? In fact, if you multiply it by its conjugate, you get 1. That is this times this over two equals one, right? So these factorizations aren't really different because both of these actually are unit multiples of two. So I've used the units to kind of be a little tricksy here, right? Do I agree with that? So that's another thing that I've got to really establish. Does anybody remember maybe in the old days, how did you show that these things are irreducible or whatever? Y'all remember using the norm? Is that anybody remember? The norm of and the norm had properties. One, the norm alpha, here I'm going to take alpha to be the element of this ring, is zero if and only if alpha is zero. These are all fairly easy to prove. Norm of alpha is plus or minus one if and only if alpha is a unit in the ring. And three, norm alpha beta is norm alpha, norm beta. And in fact, you can rip off at least this one from that one. Notice that really this norm is actually alpha alpha conjugate, right? Because it's a plus b radical negative 5 times a minus b radical negative 5. So there's where a little bit of Galois theory goes, right? And so really what you're doing to get the norm, we saw this earlier, is you multiply by the conjugates. We've already seen that this is multiplicative, right? And we looked at the signal time. But how many of y'all saw this before you darkened the doors of 85, right? At some point. Well, the norm here is particularly easy to work with because this thing is always positive, right? That makes it easy. It's easy to get the norms of all these players up here. Right. Now, let's suppose that 2 was not irreducible. That means that 2 factors down into alpha beta, right? Using this property, that means that the norm of 2, which is 4, has to be the norm of alpha times the norm of beta. But we don't want it to be a unit, right? So that means that if you can break down 4, that is if 2, if you can break down 2, if 2 is not irreducible, then it has to have a non-trivial factorization or a non-trivial factor of norm 2. Do I agree with that? Because the only way to factor 4 is 2 times 2 or 1 times 4. 1 times 4 doesn't count. 1 is a unit. Is it possible to write 2 as a square plus 5 times a square? No way, right? So 2's got to be irreducible. By the same token, can you write 3 as a square plus 5 times a square? No. So 3 is irreducible. Can you write 6? So the only possible factors of 6 are 2 and 3. We've already shown that you can't have norm 2 or norm 3. So all 3 of these are irreducible. Well, 4 of them really, just plus or minus. They are all irreducible. Now, can I have such monkey shines as I've got over here, where I'm disguising things because they're really unit multiples? Let's look at this property. Is it possible for a squared plus 5b squared to be 1, plus or minus? Well, certainly not minus, right? And the only way it can be 1 is for b to be 0 and a to be plus or minus 1. So the only units in this ring are plus or minus 1. And clearly, these do not vary by a sign, right? So there's something a little bit more concrete. Yes, these are truly different irreducible factors. Everybody okay with that? Now, where am I going with all this? I'm gonna use this as a tool in a moment. I want us to consider some ideas. Um, I'm gonna consider, these are all three ideals in this room. First one is generated by two, is the element one plus radical negative five. Second one is, three and one plus radical negative five. And the third one is the conjugate of this one. By the way, why didn't I list a conjugate for this one? Anybody know? Or did I? That's right. Two is a little unusual. This one is a conjugate because if you look, the difference in these two generators is multiple of two. So in other words, if I take this element minus two radical negative five, I get this element. So they're in the same ideal. That's not true for this one. So these are truly different ideals. The first thing I might want to do is convince myself that these are proper ideals. All right. Which one do you want to do, David? P2 or P3? Process is the same. Maybe P2, it'll be a little bit easier on poor old Jim. Plane. By way of contradiction, let's suppose 2 times A plus B radical negative 5 plus C plus D radical negative 5 times 1 radical negative 5 is equal to 1. Let's just suppose that could happen. This is, yeah, but I'm gonna do it anyway. 2A plus 2B radical negative 5 plus C minus 5D D. C minus 5D plus C plus D. So let's see what we got. I got 2A plus C minus 5D plus 2B plus C plus D. Right, 5 is equal to 1. Brady, that's a lot of variables. Fine. Let me point out. Were this to work, I just add the equations, and I don't really have to do any work here. One and two. What's the one? What's the 1 and 0? The first question should be 1. Yep. Right, so what I'm doing is Oh, okay, I see what you're saying, yeah. That's what you're saying. Correct? Yeah, you're right. But the result is the same, because all it is reverse these. This is a contradiction, because the left side is even. So P2 is proper. To show P3 is proper is a similar process. And once you know that this is proper, this is the automorphic image. P3 bar is the automorphic image of P3. So if this is proper, this has to be proper. Second claim, P2 is not principal. Okay, well, suppose, just for giggles, suppose that it's principally generated. This means alpha divides 2 and alpha divides 1 plus radical negative 5. Right? Any principal generator has to divide both of the elements generated. Agree? This means the norm of alpha must divide the norm of 2, and the norm of alpha must divide the norm of this, which is 6. Right? So the norm of alpha is equal to 1 or 2. No choice, because it has to be a common divisor of 1 and 6. But it can't be 2. Because we showed earlier that a squared plus 5b squared can never be 2. So there's no element of 1 or 2 to do that. And it can't be 1 because we just proved it's proper. So if it had a divisor of norm 1, that would have to be a unit, which is impossible. So P2 is principal, non-principal. And let me gather up some information here. These are, in fact, all are prime, in fact, are maximal, non-principal ideas. All of these. And the proof is very similar. Now, I'm going to pull back the curtain a little bit on that element-wise factorization that you saw earlier. Let me show you another trick. Um, right. Ideal be generated by 9. 3 minus 3 radical negative 5. 3 is 3 radical negative 5. And product of these two, which is 6. Right, agree? All I did is I just multiply them. But this is probably a little bit surprising, because neither one of these two ideals can be generated by a single element. But their product. Weird, right? Let me tell you what's probably obvious is this container. Right? Because notice 3 divides every single generator. So certainly the ideal generator by 3 has to contain this. What might be a little bit more mysterious is the other way. But it will suffice to show that 3 lives in this ideal. And it does, because so you have equality. So what you have here is 2 non-principal ideals. When you multiply them together, magically got a single generator. Actually, so I can keep my story straight, let's try this. It turns out P2 squared is the ideal generated by 2. The computation is just like this, and one can argue it's even simpler. Let's do another one for practice. Actually, I'm lazy. Multiply these 2 lines. Generator are here 6. I get 2 minus 2 radical negative 5. I get 3 plus 3 radical negative 5. And then I get 6 again. Goodness. Anybody, I don't know, guess what we got here? Let me try to convince you of this. I think, can we all agree that 1 minus 1 divided by 5 divides both of these, right? It's also clear, isn't it, that it divides this one? Maybe perhaps what's a little bit less clear is it divides this one, but let's check. If you have see, you never thought that all this conjugation stuff was coming in handy, but I can multiply top and bottom by and this is going to equal something crazy. 3 plus 3 radical negative 5 plus 3 radical negative 5. And then it's going to be like minus 15. And this is going to be 6. So this is going to turn out to be minus 2. That's going to be minus 12 plus radical negative 5. So that's this. So we've got this containment. And for the other containment, notice 3 plus 3 radical negative 5 minus 2 radical negative 5 is equal to 1 plus 5 radical negative 5. And now I've got a multiple 6 to help me out. So now so I can get it. So let me show you kind of what's going on here. If you look, all players here are prime ideals, non-principals. The ideal generated by six is and that factor six does not factor uniquely into elements. We saw that earlier. But the ideal generated by six actually factors uniquely into these prime ideals. And playing a little mixing game is what gives you the different principal ideal factorizations. This is you could also write it as this is going to be, well, this one is going to be the ideal generated by one minus radical negative five. Show that. And this was the conjugate of that. So the ideal generated by six factors uniquely in the prime ideals to P2, P2, P3, P3. But arranging them different ways gives you different principal ideal factorizations. Right? And so when in this ring, of course, I've only done an example, but it turns out in this ring, even though you lose unique factorizations of elements, that is, unique factorization of principal ideals into maximal principal ideals, what you do gain is you get unique factorization of principal ideals, in fact, any ideals, in terms of prime ideals, some of which may not be principal. But notice from our theorem last time, since P2 squared is 2, and P3 bar is 3, then players here, P2, P3, P3 bar are all invertible. And there is, I think, kind of one of the best. So we've seen last time that all non-zero principal ideals are invertible. Here is a good example of some invertible ideals that are in fact not principal. This is kind of important. Comes up in algebraic number theory quite a bit. Let me make the following. Here's a theorem. It's very easy, but it's useful mostly for the observation that you do. Theorem 936. What? Invertible ideals. On forms and multiple. Here, I mean, I times J is just a standard product of two ideals. Notice, if I and J are principal ideals, and their product is principal, right? And more generally, product of two invertible ideals is invertible. It's easy to verify IJ inverse, so I inverse J inverse, and R functions is that kind of. So in particular, that first statement shows that if I and J are both invertible ideals, then I times J is an invertible ideal, because when you multiply IJ by this, of course, this community ring turning to be round, you get R, which is good. Now here is a really cool theorem. This is actually another one of my favorite theorems that I think at the outset is not obvious. Any questions up front? Get to my favorite things. Yeah. Yes. But remember what it means to be. I mean, if I walk up to you on the street, let's just make our lives easier, suppose ours is variable domain. If I give you any fractional ideal, any ordinary ideal, even other than zero, I can, well, I can do this for zero too, it's nonsense. If I give you any ideal, I can write down what its inverse is. It's just defined to be everything that throws the ideal ring. It's invertible if when you multiply I times its inverse, you get all of R. It's always contained in R. If you get equality, we know that any principal ideal is invertible, non-zero principal ideal. Then that's good. But it's not clear at all at this juncture. I don't think that invertible ideals have to be general. Right? There's nothing in the definition about it, but it turns out, so this is kind of a theory. And in certain sense, it might be considered at the outset sort of unexpected. Let me give you a strong word of caution here. The converse is almost never true. Right? In fact, to say that an ideal is invertible is more general than saying it's principal, but not a whole lot. Being an invertible ideal is an extremely restrictive condition. It must be finitely generated. Finitely generated is certainly not good enough. I'll give you an example of that. Well, actually, maybe I'll do that now. And here's what can go on. Suppose, let me just take a polynomial ring of fields. Let M, I write this because it's the last one. I'm gonna take advantage of a couple of things here, I think. The first one is R's unique factorization ring. And I know that because F is a field and any polynomial ring field, and however many variables you want, is unique factorization domain. Let M be the ideal generated by X and Y. So this is a maximal. What is M inverse? This is a set of stuff in the quotient field. You got f of x, fxy over gxy, such that f over g times m is contained in R. Now, certainly, everything in R itself, every polynomial two variable satisfies it, because it's already in R, right? So everything in R throws it back into R, no problem. My claim is it's exactly R. Everybody with me so far? Let's suppose Suppose I've got something in inverse. F over G is in inverse. Well, because of the fact that this is UFD, I can factor F and G and reduce if possible until I've got the top and bottom relative to prime. Now, what this means is F over G times X is R1 and R. And F over G Y is R2. Because you gotta knock, I mean, both of these guys are in M, so you've gotta knock both of those back into R. So what does this mean? Well, let's play with this. This means F, X times F is equal to R1G. And Y times F is R2. What do you know about the status of X and Y and R? You know they're prime, right? X and Y are both prime elements in this ring. Right? So, X divides R1 or X divides G. And Y divides R1 or, I'm sorry, R2 or Y divides. Uh, Now, if both X and Y divide G, then you've got a problem. And so that means XF equals XYG prime, YF equals XYG prime. Well, and this means that if you cancel the X, this implies that Y divides F in the first equation, which is a contradiction. Right, because here the X is erased, now Y divides F, but it also divides G, so you can work your way through the other cases of this. That's time, I'm going to stop here. Let me just say et cetera, that's a little handwriting. But you can go through these cases and show that show that G divides F. And so M inverse is equal to R. So if you want to select all the fractions that throw M into R, it's just R. But now what happens is, so M inverse equals R and M in inverse, which equals M R, is M, which is split between an R. So M is not invertible. Like I said, invertibility is a pretty stringent condition, so if you just find some generated ideal, it's probably not invertible. But this is kind of a Ruby theorem because any invertible ideal actually has to be finitely generated. So proof. Inverse equals R. Let me deconstruct what that means. That means the element one has to be an I inverse, right? So there exists A1, A2 to AN in I, and B1, B2, BN in I inverse, such that A1, B1 plus A2, B2 plus AN, BN is equal to 3. So what does this tell us? Well, I claim that these elements that came up in my relation that gave me 1, those will suffice to generate I. And so actually, this is, I like this as an example of a proof showing more than I stated, because actually this gives you a technique for finding what's the least number of generators required for A. It's what it should go hand in hand with the shortest n I can find, such that I get an equation. That's kind of neat. So, let's prove this. Certainly, so this is an R module, right? And each of these AIs is in the R module I. So over R, that's the easy way, right? But what about the other way? Let C be an I. Notice that I'm multiply this equation by Z, and I'm going to do it this way. See, how do I want to do this? Right. That was just like a little artistic rewriting. And notice, well, can anybody, why did I write it this way? Well, notice that B I is an I input, and C is an I. So BIZ, where does this live? It's an R. So C is in, R model. Generated by A1, A2. Right, because all those things that are multiplying my generators are actually bona fide elements of R. Here is, I am going to give you, I'm going to give you the statement, three more things I'm going to state for you, and then Jared will help you out with it next time. Theorem. This is another important characterization of invertibility. What are the domain and I, a fractional ideal? If I is invertible, then it's locally principal. Then I P is a principal ideal. Clause. This is what we call a fractional ideal. If it's invertible, then it's locally principal. So the localization of the ideal is principal fractional ideal for our localized P. If I is finitely generated, then converse also applies. So if you have an ideal that is finitely generated and it's locally principal, our localized P is always principal in our localized P, then it's convertible. 9.3.9. This is very let R be commuted one, then R is equal to the intersection of our localized M. Given one, then R is equal to the intersection of its localizations at maximum or maximize M. That's a short proof. Actually, I want to speak that way. That's all I care about anyway. Let me give you this final theorem. Just put it next time. And I wanted to do this here because this kind of comes full circle with what we're talking about today. Let R be a domain, following the protocol. Number one, every non-zero fractional ideal bar is vertical. Two, every non-zero ideal of R is invertible. So if the non-zero ideals are invertible, then that extends to fractional ideals. 3, every proper non-zero ideal is a prime ideals. In fact, it can be any. So this is like UFD only for ideals, right? Everything's product of prime ideals. Number 4. R is the theorem. It can be closed. MR is less than 1. That means either R is a field or all non-zero prime ideals are maximal. Finally, R is the theorem. And RM is in the theory evaluation. Well, max. Any domain satisfying one, hence all of these conditions, is called a Dedekind domain. And you can thank me at this point because I think there's less than 100, but well over 50 characterizations of Dedekind domains in the literature. I will quit there, right? But there's lots and lots of different things. I will let you all discuss this next time. I hope to see you all on Friday, Saturday, but I've enjoyed having you as class, and so you get the good luck of not having me for the last day. So, any questions?